Hello Panther and welcome to our new video. Today I will focus on the derivation or deriving the Magnus Force directly from the Navier-Stokes equations. So let's begin. It will be very difficult maybe for some of us, but I think it will be sufficiently explained in detail, so I will explain what is going on, and the solution is easy to follow. Let us begin with introduction. What is the Magnus Force? Magnus Force, or sometimes called just the Magnus effect, is a force exerting on a rotating ball in a moving fluid. When a football player or a soccer player, a better soccer player, kicks the ball spins, it curves in the air. And the effect, the Magnus effect, is describable in terms of Magnus force exerting on the ball. When there is a rotation, I will call it omega, and with the vector omega, its magnitude will be omega, and the normal vector omega hat. I will use omega hat only in this case. In every other case I will use omega vector, this whole omega. You can see that the Magnus force is proportional to velocity of the fluid, is proportional to the rotation, bigger curvature, bigger force, is proportional to the density of the fluid and the dimension of the ball, a cubed. A is the radius of the ball. This is 2a. Reynolds number is defined in this way, but I think never use it. But anyway, there are actually two Reynolds numbers because there are two characteristic velocities. You can think of them as being: the first one is the velocity at infinity, the moving fluid, the ball is stationary or rotating in the same place, and the second one is rotation around the ball, because the velocity of the fluid on the surface is exactly r times omega, where r is the polar distance. So, and this is a dot product with r, and you can see that there is a vector product between these two vectors, so the force is coming in this direction to behind in the direction of the paper. So let us, and when these vectors are parallel, there is no Magnus force. So let's begin our discussion. I've listed one formula which we'll derive. It's the formula for the pressure from the Magnus effect, Magnus force, Magnus effect pressure, and is this. It's a scalar because there is vector product and scalar, and the dot product, so it's just a scalar, and this is a vector because there is vector product there. Let us begin with simple equations. We will use the first one is the equation as always, equation of continuity in the form of the fluid, incompressible fluid. It's called it is just the gradient, or the divergence of velocity field is 0. What are the boundary conditions for the velocity field V? The boundary conditions are V at r is equal to a must be polar. I will call it just r with the apostrophe because it's the distance, polar distance from this axis omega. So it's like r omega distance times omega, and velocity at r is infinity should be v infinity defined vector, which is in our case, in our coordinate system, because there is z, it's just v infinity, which is the magnitude of the velocity at infinity, times z hat, which is z hat is unit vector, or z z hat, yes, z hat, unit vector in this direction. So the second equation, it's basically the Navier-Stokes equation, but I will derive it anyway, because let us write equation of motion of the fluid. Mass times acceleration is equal to force. There are no forces in this coordinate frame, plus divergence of the surface forces, which comes from this stress tensor. So, and if you remember, d over dt can be written as the partial derivative plus the dot product with velocity vector and velocity field, and gradient of the velocity field is basically material derivative. If you substitute in to the material condition, which reads that for incompressible Newtonian fluid is minus p operator identity matrix plus eta gradient of v plus gradient of v transpose. If you substitute in, you will get stationary, because I will dismiss this term, I will cross it and forget this term, because I will assume that the fluid is stationary, the flow is stationary, there is no turbulence there. So you will arrive at this equation, which is Navier-Stokes equation. You can check it, but this is the correct form. It's basically telling this, and this should be the Laplacian of velocity field. This is our Navier-Stokes equation, and I will solve this equation. Again, the method of solving this equation, I will use Edomian decomposition. But first I will divide this equation by eta dynamical viscosity to get this equation where alpha is small parameter. So there is a minus p plus Laplacian of v, where alpha is defined as rho over dynamical viscosity eta. So this equation I will solve for small alpha. So let us write Edomian decomposition method. Edomian decomposition. This method is based on decomposing the solution into one where alpha is 0 and second one where alpha is linear order. So let us write the conditions, the functions. The first function, unknown function, is the velocity function. I will write the velocity function as v0 plus alpha v1, where v1 is the first correction or problem. There is a pressure function, which is, again, you can write it in this fashion, similar fashion as before. What are the boundary conditions? Yes, well, I will discuss them. The boundary conditions are v should be at r is infinity, v infinity, but what is v0 actually? If alpha is 0, so this equation reduces to this equation for the Stokes flow. So this equation is just Stokes flow equation, and this equation is linear. So that means you can compose the solution v0, you can decompose to two solutions. The first one is v0 translational, and the second one is the v zero rotational, because you can always make superposition of these two solutions. V0t is just basic Stokes solution, which is the curl of psi 0 translational, which is rho r, where r is function of rho, times phi hat. And rotational solution is, again, you can find it in the section on the rotating sphere in stationary fluid. So you can check these two videos and make yourself comfortable with these solutions. They are known pretty well. This part is at infinity equal to V infinity, so this boundary condition checks for this part, and for r is equal to a it's 0, and this part is quite the opposite. The second boundary condition is satisfied. At r is equal to a, this holds, this part is hold for this, and for for r is equal to infinity, this term will vanish. You can check it in the video that it's not O1, it's OR 1 over r. I think it's 1 over r cubed, but never mind. It basically vanishes at infinity. So next P0 can be also decomposed in two solutions. P0 can be also decomposed in two solutions. The first one, it's the solution from translational part, it's Stokes solution, and the second is from rotational part. And remember, in the video I proved that this part, it's actually 0, so it's only rotational part, only translational part, and this is a familiar term, -3 V infinity eta a over r over 2r cubed times z. This is very familiar term for this solution, and also V0t, you can be also familiar with it. It can be written as the curl of some vector field psi, call it psi 0t, where psi 0t it's rho r phi hat. Again, you can write it as rho r is a very familiar term. It's I think this is the term for r. So this is the solution for the 0 translational. The boundary conditions for the excited fields, vector field and scalar field for the pressure, are very simple, because the boundary conditions are satisfied immediately with this part. So these terms has to vanish. There are 0 V1 and P1 is 0 at r is equal to a, and r is approaching infinity, so it has to vanish at infinity, it has to vanish at r is equal to a. These are boundary conditions for V1 vector field and P1 scalar field. Next, I will substitute in this form of solution, but with this decomposition into this equation. You can substitute in, and you will recognize that the terms V0 and P0 matches and vanish. So I will write just the first order term in alpha, which will be this. This is our equation before substitution. This decomposition, only this part is just dot product between these velocity fields, and there is minus 1 over eta gradient of the pressure 1, and I'm sorry, there is no alpha here because it's a linear term, plus its equation we are equating the linear term of alpha, so there is none, plus Laplacian of v0 v1. Again, you can substitute in this kind of solution VOT plus OR, so you will get this 4 terms. You will get this 4 terms. It's just very simple derivation, but I will do it anyway. OT, gradient of OT, this is the first term, plus the second term is O rotational part, plus VO rotational part, plus the cross terms O translational part, dot product with rotational part, plus the opposite, so 0 rotational part, dot product with gradient of 0 translation part, and this should equal to this right hand side. You can immediately see that this equation is linear because there is known function, so we can superpose the solution for the pressure and for the velocity field as a sum of independent solutions. You can immediately see that this term, this equation where this vanishes, so if this is OT or 0t and 0t, so the solution for this problem is the lamp solution I've discussed in the last video, and solution for this problem where there is only 0r rotational part and 0r is the excited rotational solution for the low Reynolds number, which I've discussed in the previous video. So these terms can be solved by this substitution, superposition. I can call it superposition. When P1, when P1 is equal to, you can decompose it, and when P1 is equal to P, the pressure from excited rotational part plus from excited translational part from the lamp solution, and plus this is 1 because it's not the pressure 0 but the solution of the problem, the first approximant, the first iteration. So this is 1 and 1 rotational and translational part, and then there is another function P. I can call it P1M, like P1 Magnus term, which will arise from the problem. And again, for the velocity field 1, which is on the right hand side, I can write velocity 1r, which is the solution for the excited rotational part from the previous videos. And again, there is a lamp solution for V, and I can write V1m as the correction, the unknown function. If you substitute in this equation, you will get that this will match up. These two terms, rotational terms, will match up with this term, and these two terms will match with this term. So overall, the equation we will be solving is this: V0t dot product VOR plus V on the opposite gradient of VOT and this is equal to minus 1 over eta Laplacian P1 m plus gradient of this and plus Laplacian of V1m. This is the equation we will be solving, and the solution for this is going to be crucial when deriving the Magnus force itself. If you remember what pressure was, actual pressure is the alpha multiplier of P1, and there is a formula which we are getting to, and this is the solution for the pressure with alpha. So alpha times P1m is equal to this term, is going to be equal to this term. This is the solution. I can write also the solution for the vector field, velocity field, but it's much more complicated. But only the solution is only in terms of rational functions, so it's very easy to write, very easy to implement the solution in computer, or you can compute it with it, Magnus Force, for example. It's not so hard, but the computation is, I think, a bit messier. So now we have to compute these two terms. These terms are going to be very complicated to derive. So let us first write the solutions in terms not of phi hat vectors, but in the cross products between the omega vectors, z hat vectors, and the position vector, which is defined as r multiplier times of r hat unit vectors. So let us write this equation for translation apart. For translation apart, you are familiar with the solution. It's just rho times r, where rho is polar radial coordinate, and there is also phi, and you can check it, but these two terms can be combined in this term, c cross product with r. This is position vector. Why? It's very easy to do, because in our table, which is over here, z cross productive r is going to be z cross productive r sine theta times phi, and I think this is going to be, yes, it's in this way. It's a positive direction of phi hat vector, so this is plus phi times sine of theta, but sine of theta is rho over r. But if you multiply it with r from our position vector, because our position vector, as I told you, is r multiplier of r hat vector, then you will cancel with r and you will get exactly this combination. So this is the equation for the translational part. And again, for rotational part, if you remember, rotational part, zero rotational, is going to be what? I think it was. Oh, I'm sorry. This is not a whole point, because there should be a curl of this. I'm sorry, but there is a curl of psi. This is a psi zero translation vector. So this is curl of this. These two are equal. And for rotational part, the solution looked like a cubed divided by r squared omega times rho phi hat, and I think there is cubed. So this is the solution for this vector field, and again it can be, and this is the solution when omega omega is in the direction of z hat vector. So you can check it, but this is the solution for the omega times z hat cross r hat vector. If you combine this, you will get the phi vector in the direction of z vector, and this form will remain if vector omega, amazingly, it's in the different direction. Why? Because this term does not depend on any coordinate which is not symmetrical, radially symmetrical, and this again also is not depending because there is r, so only dependence is from this vector. You can rotate with the ball and make a different set of coordinates, and I can also choose the coordinates when z is in the direction of omega. So this is the term of the solution. So this is a general term of the solution. So our solution, this is only in z direction, where omega is omega z hat, and where omega when omega vector is omega times omega hat in the arbitrary direction, the solution will remain in this particle form. So it's a cubed over r cubed times omega vector cross product with r vector. Now we are dealing with the problem of computing the curls of this particular form of vector cross products and the functions. Well, for this purpose we have to make us a table of all formulas we are going to use to compute various vector calculus identities. Now I will show you the table of the formulas I will use later in this video. The formulas are here. These are formulas of r vectors, position vectors, z vectors, which can be also in this changed with omega of or any other constant vector in all these formulas except the first one. A, B and C are constant vectors, so these are the formulas we will be using, and I've decided to cut the video in the part where I'm deriving the formulas in this table. You can access the derivation in separate video, I think, and I will just use the formulas and you will see where they can lead us. So let us continue in the derivation of these parts. So what are they equal to? So let's compute this terms. So for a starter, let us compute the gradients of VOT and VOR. But you can remember that this is also just some operator, differential operator of something. In this case, it is a curl of something. So the curl of this is what? The curl of this is if you take curl of this, the gradient of this is r hat, r prime times r hat, which can be written as r over r, and r is position vector. From now on I will use only position vectors because they are easy for them. The formulas are much easier. So this is z cross r, and the second term is plus r, and this is curl of z cross r. Now it's time for our formulas. So I can let it in this form and don't bother with computation. But this can be simplified. So the first term I can let it in the form of curls, because we have formulas also for this, and there is plus 2 times z hat r. This is the second term. Why? Because this. And what next? Let us compute curls or gradients, because you have to take gradient of this. So we have to compute gradients of OT, VOT, and VOR, V0T and V0R, translation or rotational solution. Part solution. If we take the gradient, you will get gradient is acting on this term, which means its derivative times r hat. So this is going to be just 1 over r, because r hat is equal to r vector divided by r. Times r vector times this vector, which is r cross z cross r, and you can let it in this form. The second term is a gradient of, you have to take gradient of 2 vectors. The second one is this, or the first, let the first form in this form, the scalar in this scalar, plus take the gradient of this. And I think in our tables there is such a gradient. It's this. It's 2 times r z minus this, so I think it will be just plus r prime over r times 2 times the first was r z hat minus z dot r vector times identity operator, and the last term is coming from here, taking gradient of this, which is 2 times r prime divided by r times r. The first should be the scalar from the scalars, and the second is z, and there is no second term as in this, because Leibniz rule, will apply, but z is constant vector, so its gradient is 0. So this is the resolution or the solution for VOT. For VOR, interestingly enough, the form is you can compute gradient of V0R very easily, because it's gradient of this, which is derivative, which is minus 3 over r to the 4th power, respectively to the 5th power, times r hat, r vector. So it's minus 3a cubed r to the 5th power r omega cross r, and the second term is from here. The gradient of this is just minus I cross omega, which is minus a to the 3rd a cubed over r cubed a I cross omega vector, which is the formula from here, minus this. So then you have to compute the dot products. So you can do it. It's very easy to do, because you just take dot products. And if you do that, you will get for the VOT dot V the gradient of V0R, V0T and V0TR, it's easy to show that you can write it in this. The formula is this. This is the result, a cubed over r to the 4th power r prime times r cross z cross r cross v cross omega minus 6a to the a cubed r to the 5th power omega cross r z hat r over cubed z hat cross omega. This is the result for this. Many terms will vanish. As you can see, there is z, and there is this vector. It's perpendicular to r because it's crossed with r. So if you dot this term with this term is proportional to r. So this will vanish. So the only term which remains is minus this times this, but this is going to be what? This dotted with identity vector is the vector itself, which is this vector. Cross this product, this is the first term. And you can take this vector and dot it with the first one. It's minus 6. And there is z vector dot r, which is over there, and this is dotted with this, which is going to be this, because z dot I is z, so it's z cross omega. Very easy, I think, not so complicated. Again, for the second part, you have to compute V0, V or VOR, with the gradient VO translational, VOT. And this is again not so complicated, because I will write it again and then I will explain what I've done. R prime to 4th power omega cross r minus a to this power and r 4th and there is omega cross r and z dot r. Well, and I'm sorry, I've made a mistake because there is a missing term. There should be minus z hat times r hat, because this derivation is not correct. There is an additional term minus z and r vector in the table. So with this correction, it's easy to see that you have to take dot product of this with this, and as horrible as it sounds, it's not so terrible to compute it, because this vector is orthogonal to r, perpendicular to r vector, and these are just r vectors, and this is also r vector, and this is r vector. These all are proportional to r, so this will vanish because the dot product of two perpendicular vectors is 0. This term vanishes, this and this, so only remaining terms are from this, which is omega cross r dot z hat and times dot z hat, and r will remain. So this is this term with minus from here, and r squared r to the fourth power. This term is there, and there is an additional term coming from this, because if you dot this part with identity, you will get just this vector. So this vector is here present, and this is a scalar as it was before, and this term is the same as r squared and r prime. Yes, it's the same. So next, move on. If you sum these two up, you will get the left hand side. I can do that, but it's not necessary, I think. But I will do that, and I will denote some new quantities. This I will refer to left part of the left hand side, and this is the right part of the side, or I can just write summation sign. If you sum up these two results, you will get this. It's minus a cubed r prime divided by r to the fourth power, and there is z hat cross omega times dot r. From this part, from I think this part, but I'm not sure, because these are only vector identities. You can compute it yourself. It's not so complicated. I think it's from this part, and again there is back minus cap, so it's this identity used on this term, and this will show up minus 2a cubed r prime over r to the fourth power plus 3 times r over r to the fifth power, and there is omega vector cross r and the scalar z hat cross dot r minus the last term, which is a cubed, and there is r prime divided by r squared plus 2r divided by r cubed. You can compute it yourself, it's not so complicated. You can show this term is just sum of these two with back minus cap identity. vector identity of vector products. I will denote this term as u. This is only just function of r, and this part as a v. This part as a capital V function. And then if you take the curl, now I will take the curl as always, as before in all my videos. I've always taken the curl of this equation to get rid of this term. So if you take the curl of this equation, this will vanish because curl of the gradient is 0. So you are only left with curl of the left hand side is equal to Laplacian of curl of v 1m velocity field. You can always switch these two because Laplacian is scalar differential operator. So you will get this particle equation. The left hand side is if you take the curl, so that means that taking curl of this part, which you take curl of this part, which is not so complicated to do because it's just taking this curl of this is gradient of this, which is proportional to r hat crossed with this is 0. Curl of r hat is 0 also, so you have to just take gradient of this and curl it with this. And as you know, a gradient of vector dot where it is, gradient of vector dot r, position vector is just the vector itself. So this will be just minus a cubed over r to the 4th power r prime z hat cross omega cross r. This is the first term, and also for the rest terms. For the rest terms, you can always do the same. There is derivative of this, and you have to take curl of this. Okay, I can show you the tables, but the first term is 2 the gradient of this times u times r vector cross this, so it's cross r cross r, and there is z hat dot r position vector, and the curl of this term, which is going to be over there, curl of this term, which is this 3 times omega minus this, so it's just minus 2a cubed times u, just a function of r, and there is 3 times omega times z hat dot r position vector minus r vector times times omega dot z, which comes from the second part. Then I will compute this as a, because this is constant vector, so you have to just compute this term will be just minus a cubed over r times v prime times r position vector cross this, so it's r position vector cross z hat cross omega hat. So this is the left hand side. These are just functions of r, u and v and r, and this is equal to, Laplacian or curl of Laplacian of v1m. This is the equation we have to solve now. It's not so easy equation, but never mind. Again, as before, we can guess the solution, because you can rewrite the left-hand side of this equation in much more neat form. I will just write symbols for this, and you can compute it by hand or use a computer to do it. I've used a computer to do it instead of me. So the result is, if you do that, all these vectors can be decomposed in 5, or no, I think not 5, 4, or just a finite number of types of vectors. And now I will write them here, the form of the solution, form of the left hand side, which is this. Phi 1 var phi, or this phi 1, 2 and 3 and 4 respectively are going to be functions of r which are known. I can write it, or I have computed in my computer, so I don't know them, but you can compute them. I will leave this as an exercise, but it's very messy. You just have to use the buck minus cap rule to these, and to get basic constituents, basic multiplies of the vectors. And the vectors which are respectively going to be, if you decompose them, are these are the combinations you will get if you decompose this left hand side. There is r vector plus there is second function of just r, and there is z hat dot r omega, plus the third is omega dot r z hat, and the fourth one is omega dot z hat times r vector, our position vector. So this is the form of the left hand side, and this has to be a curl of Laplacian of V1m field. Now I will guess the solution as always I've done, and the guess will be this. This will be my guess. I can guess that V1m is some curl of a function psi 1m, or just psi. Don't bother with psi 1 and psi 2, etc. So it's just psi. And the first equation, the divergence of field v, velocity field, is satisfied immediately. Now let us guess the form of psi. I will guess this form, and you will see that it will lead to solution. But first, let us substitute in this equation. So this will be just double curl of a curl of Laplacian, because you can switch Laplacian with the curl, so it's a curl of Laplacian of psi. I will let it in this form because no one said that gradient or divergence of psi is 0. If it isn't, you cannot use just simply that double curl is equal to minus Laplacian, because there is the second term, its gradient of divergence. I think it's not the Laplacian, the second type of operator, the second combination. So I will use this form. So our guess guess is psi is equal to k is some function times the first vector, which is omega times z dot r, plus L and the second vector. It's convenient to guess the solution in terms of the left-hand side, or these two functions, or these two vectors. So it's z hat times omega dot r. So this is the second vector. Now you have to compute this beast, the fourth order operator, and then you will match up these functions with the resultant two functions, and amazingly it will lead you to 4 equations, but they are not independent. They are not independent, and the solution exists. And for the sake of argument, I will just compute the first term, this operator applied on the first term, so to show you that how it will produce these 4 constituents. And the second one can be written immediately using the result of this one by only switching omega and z hat, because we are dealing with operators and our tables are invariant with respect to choosing a vector. These are constant vectors. So let us first compute the Laplacian of this part, just this part, Laplacian of k omega z hat dot r vector, and as you know it's Laplacian of k, then this plus 2 times gradient dot gradient, so it's 2 over r k prime. 2 over r, 1 over r is there because we are dealing not with r hat but r position vectors. So it's r position vector times gradient of omega z dot r plus k Laplacian of omega z dot r, and all these terms, these two terms are in our table, so we can use the table and see that this term is here, so it's just the same term as before, and Laplacian is 0. So this is the same. This whole term is just this. That was easy, and this is 0 because Laplacian is second order and there is first order in R. So it's just a Laplacian of k, which is k double prime plus 2k prime over R. And there is another 2 from this, and this is the same. So it's 4 times omega times z hat dot r, which is exactly from this term the same. And as you know, this operator was r and q. In this regression you can write for this, for example, I don't know, k1, or it's not so imaginative, but you will get the point. But you can see that it's the same multiplied, same vector here. Then you have to take the curl of this and another curl. If you take first curl of this, it's k1, just some function of r, and there is z hat dot r, and this is going to be what if you take, and there is k over r prime, and there is r curl of omega times z hat dot r position vector plus k1 curl of the second part, which is omega z dot r. And again we can use our tables to show you that this part is just omega times r, and this is z cross omega, so this whole thing can be written as minus in the order of the tables, 1 over r omega cross r times z hat dot r prime minus k1, and there is omega cross z hat. This is this term. I will use another paper, so I will move it this way, and hopefully you remember what is there on this. You can check. We have computed the curl of this, so you have to compute another curl. So you have to compute the curl of k1, or this part, which is derivative, and there is r. So it's... Oh, I will just rewrite this so you can see it clearly what is going on. So I will just rewrite the last line. So it's k prime r and z r minus k1 omega cross z hat, and this is gonna be what? This term will show up 1 over r k1 prime over r prime, and r cross this, which is omega cross r times what? Z dot r, and you have to now compute minus k prime over r, the curl of this term. And again, in our tables there is also curl of this term, because it's over there. This is a curl of this term, and it's 3 times this and this, so it's 3 times omega times z dot r minus r omega dot z, and this is not the last term. The last term should be minus this term curled, so it's 1 over r k1 prime r curl of omega curl z. And as you can see, this term, if you rewrite it, is proportional to omega vector and zr, which is exactly omega vector zr. So this is this term, and there is hidden also this term. This term contains omega z rz and zr omega, which are also these 2 terms, the second and the third vector, and this term contains contains also the first, because there is also proportional to r times r omega dot r, which is over here, and this term is hidden in this. So these are also all terms which you can match with above solution, and I think I think some of them will will vanish. I think this term, one of these terms I think is 0, one of multiply, but never mind, you can check it yourself. So you can see this is coming well, and again, so this is the right hand side of this particular equation. Now you have to compute. Now you have to compare the coefficients of these functions, with these coefficients, and the result of these coefficients. And again, you can compute it yourself, and solve them with respect to k function and L function. I will left this as an exercise to a reader because it's very complicated, messy algebra, but if you do that, you will arrive at this solution. What are the boundary conditions? I've told you that V1 is curl of this, and V1M has its own boundary conditions, which are, it's just 0. It's 0 on the boundary, so to velocity to be 0, it must be that because the psi, the curl of this is proportional to the first derivative and the zeroth derivative, the function itself, it's sufficient to have these boundary conditions to vanishing condition. The boundary conditions for k and L functions are k should be 0 at a, and also its first derivative should be 0, and for L it's the same condition. And if you solve this, and also this is what term, this is linear in R times the degree of k in it, so the derivative is, the velocity is just a degree of k and L respectively, so k cannot be a degree more than 1 over r to the minus 1, and r cannot be a degree more than 1 over r, so these two are proportional to 1 over r, no more than r over r. They can be 1 over r squared, blah blah blah, 1 over r cubed, but not constant terms. So these are the boundary conditions. You can see them. It's not so hard to recognize, or not so hard to compute these functions, and I will present you just the results for the functions, and it will lead you to the end to this video soon. So k and L as a functions, k as a function of r is equal to v infinity a cubed over 96. These are my solutions. They can be wrong, but you can check me if they are. There is minus 3a cubed plus 22a squared r minus 45 a r squared plus 36 r cubed, and L of a function of R is there is the same coefficient, so this is 96 R to the fourth power, and these coefficients are just 3a cubed minus 14 a squared R plus 9 ar cubed plus 12 r cubed. You can also calculate the pressure, and the method is the same as the video before on the lump solution. I will not repeat the method, but I can just tell you that it's going to be very simple. You can rewrite this as a function of r. P is a function of r. You can switch this on the left-hand side, complete Laplacian yourself. This term is known here. This sum is here, so you can just substitute in, and then you just compute the integral of this and multiply it with minus eta, so you will get the pressure, and the pressure for this P1m is equal to, or will be equal to, minus V infinity a cubed times eta divided by 4r cubed, and there is 1 plus. You can compute it yourself, because otherwise it will take so much time to compute it in hand, just because it's complicated. Not so complicated, but it's messy algebra, so I will skip this part. Oh, I forgot to mention these are Euler equations, or equations of differential equations of Euler type, so the characteristic solution is r to the lambda power. So next we are going to the end of the video, because now we have to just solve for the force. As you already know, if we have a surface and we cut off element of this surface and denote its surface area as ds, this surface has an outer normal attached to it, and there is a force acting on this little element of surface. From the definition of stress tensor, this force associated with normal vector is defined as a dot product between stress tensor and unit normal. Let us split our problem into two parts. First, I will remind you that stress tensor is for Newtonian fluid given as this expression. So for the force we have, for the pressure term, just the pressure term, it's a minus P, and there is n dot identity, which is just n, and for the case of the sphere, n vector is just r hat vector. Again, I will write P over r like this for the sake of continuity with the notation. And this should be evaluated at a, and then at r is equal to a. So then you will get the elemental force term. which is for the pressure. You've seen the pressure is here, so for the pressure you will get this is minus, I will substitute in this expression for the pressure, and A is equal to A, R is equal to A, so you will get minus will cancel out, and this is 1, and this is 1 minus 1 is 1, 3, 4, 3 over 8, there should be 3 over 8 over A, 3A cubed over O, which is V infinity eta over A over 8 times A times this vector, or this scalar, but I will multiply it with this vector soon. So this is R. Then you have to integrate the force along the surface. So if you integrate the force along the surface, you get actual Magnus Force and just pressure term, pressure contribution. And for us it's simply 3 V infinity eta over A. This is constant, even this vector is constant, dot, and integral should be computed, can be computed this way, and there is surface R is equal to A, and there is we are integrating a tensor, and just to remind you how to integrate this tensor, this is very easy tensor to integrate. So I will use the technique called coefficients equating, because this integral should because we are integrating R as a vector pointing out of the sphere, and from this vector is another vector in the same direction. In the same direction. We are integrating this tensor. The resulting tensor cannot be dependent on any particular direction. So the only option is that this result is some multiple A of identity matrix. If we take some operation which is linear to these two, we are going to get the A. This operation is trace. If you compute trace of this, remember that trace of any tensor or double tensor, I will just write A for double tensor, is just some AII, where I spans the whole dimension. So the trace of RR is just RI, which is x plus yy plus zz, which is r squared. In the other way, trace of tensor, which is split into two parts, is just their dot product. So this should be can be interpreted, squared. This can be interpreted as the dot product, and this holds for all these. The second approach is to take dot product in the first place. So you can take dot product between these two vectors, which is r squared. In the case r is equal to a, this is a squared. So if you take trace of this relation, you will get integral of a squared ds. This is the surface of the sphere, which is 4 pi a squared, because r is a, and this should be a times trace of I, which is the same as divergence of r, or in other way the sum 1 plus 1 plus 1, which is 3. From this you will get that A is equal to 4/3 pi a to the 4th power. So this force will be equal to 3 will cancel out with this. 4, oh, there is 8. I'm sorry, I forgot 8. There is 8 times 4, which 1/8 times 4 is 1/2, so it's 1/2. A cubed, because there is a to the 4th power, times v infinity eta, and there is identity matrix dotted with this vector, so the result is just this vector. And this, if I can remind you, in the beginning of my series, I have written this equation for the force, and you can compare it, this equation, with this one, and you can see they are the same. Yes, they may look like different because there is, oh, I forget pi. There should be pi, because this integral is equal to 4/3 pi a to the 4th power times identity operator. So this is pi is there, a cubed is there, v infinity, yes. Omega times omega hat is omega. Vector z hat, yes, they are the same. But there is rho and there is eta. But remember that this result is the expanded, is the first linear term in alpha expansion. I should write 1 instead of mp here, and actual force with the right coefficients is alpha multiplier of this, so it's alpha is rho divided by eta, so instead of eta there should be rho, and this is exactly this formula divided by 2. So we have seen that pressure term contributes to actual whole force with 1/2 contribution, 50%. Interestingly, the second half comes from the velocity field. I will skip one part in this derivation, but I will derive also this part. So now for this was pressure term. Now I will derive the velocity, the term from viscosity. And it's this. There is also this mysterious force. Oh, not mysterious, the surface force per element area, per unit area. It's going to be this n hat dot sigma matrix stress tensor, and this is according to this formula. It's eta r hat dot the gradient of velocity field plus gradient of velocity field transposed. Interestingly enough, we know the formula for velocity field, which was its velocity field. Oh, I'm sorry. Velocity field was just the sum, the curl of the summation of 2 of. But this is. Oh, I forgot. This is computed in this in r is equal to a. Now we know that velocity is curl of k omega r z hat dot r plus l omega z hat omega dot r vector. Yes, that's it. And if you remember, we have to compute it at r is equal to a. So the only derivative which will survive is first from this, because the second derivative will apply on k and k prime, respectively l and l prime terms, and the k will vanish because it produces k and k prime, so which is 0 because of the definition of k, boundary conditions of k. So the only terms are from the derivative of this, so this is going to be 1 over r k, this is gradient of k times r vector, position vector, cross omega, and there is z times dot r plus 1 over r l r cross z and omega dot r position vector. This is our, oh, there should be derivative. Oh, I forgot to mention that, oh, and the second term is what? The second derivative must apply only on k. Why? Because otherwise k and k prime is 0. I've told you about it. So if I compute just gradient of v, I have to take a gradient of this, which is 1 over r squared k double prime times r, and there should be r cross omega and z dot r plus 1 over r squared l double prime r cross z hat omega dot r vector. Now I have to add this term to our formula, which means to switch these two vectors and these two vectors, but it's not necessary because you have to take dot product from the left side, and this term is perpendicular to the r hat vector, so this term will vanish if you dot it with r hat. So this force is going to equal to eta. There is eta and there is r yes, there is r dot r, which is r hat dot r vector, which is just r, so this is 1 over r, which is a, so it's eta over a, and there is minus k double prime omega cross r, and there should be r dot z vector plus minus 1 l double prime z cross r vector, vector, and I will switch these two as well as, oh, I'm sorry, as well as these two I've switched. So this is going to be r, yes, this. Now I will integrate this whole thing because actual force is equal to the Magnus force from the viscosity term is equal to the integral, surface integral of Tn with respect to ds. And if you remember, these are constants and k is evaluated at a, so this is also constant, this is constant, so only term, this is also constant, which is varying is this tensor, this particular tensor, but we know also this tensor, but we know its value if you integrate it, because it's 4 pi, and there it is, 4 pi over 3 times a to the 4th power times identity operators, so this should be 4 pi eta a to the this one cancel out, so to the third power divided by 3, and then there is identity operator between these. Identity dot z is just z hat, and the cross product is omega cross z hat. You can switch these two and write it in the order like z hat omega, and similarly this is z hat right away z cross omega vector, so it's right away z cross omega, and this is identity times this, and this factor is here, so it's just k double prime minus L double prime all in brackets. Now you have to compute this at r is equal to a, so that means you have to substitute in the second derivative of this and subtract, and I can also do it in hand, but I will leave this also to the reader because it's not supposed to be the video about differentiating a rational function. So this is 3/8 times v infinity you will get from the differentiation at r is equal to a. It checks because this is order of I to the 6th power, this is 4th power. You will differentiate it twice, it's 6 and 6, which gives us 1 a to the 0th power, just a to the 0th power, and that means there is some constant. I think this constant is 1/16, and this constant is minus 5/16, but I'm not sure, and there is v infinity before these constants. Now that means that this force m eta is this cancel out with this, and this is going to be 2, so it's 1/2 v infinity eta a cubed, and there is z cross omega vector, which is the same as this term, and I forgot pi 3.14, so this is the same. So if you sum these together, this again should be 1 here, because you have to multiply it with alpha to get the force. Actual force is so fnp plus fn eta, which means alpha times sum of these two, but these are the same, so but I am going to write it anyway. 1mp plus f1 vector, these are all vectors, 1m eta, and you will get if times eta divided by times rho divided by eta, so this will replace this, we can replace by rho, so it's 1/2 plus 1/2 is just 1, so it's v infinity rho a to the a cubed pi z hat cross omega vector, and this is Magnus Force in its whole glory. So this is the Magnus Force. Again, it's the same form as I have shown you on this infographic, so it's this equation is this equation. So I hope you enjoyed this video. This video was a bit different than the previous videos, because many of it is left to the reader. I definitely recommend to do the exercises and recommend to solve the differential equations, because it's very interesting to see that all 4 equations with 2 unknown functions are solvable. I was astonished by this result, so I hope you will also be astonished by this magnificent result, which is Magnus Force. I am not sure whether the velocity field given here, velocity field given here, it's KL. These are the functions for the velocity field, and the velocity field, I think we have defined, or velocity field, I think we have defined it somewhere, but again, velocity field is over there, velocity field. I'm not sure whether it produces a moment, so you can compute a moment generated by this force, or I can compute it in sequence. I think it's 0, but I'm not sure whether it's true. It may be some number, but you can check it yourself. Again, as always, I will slide all from the Magnus Force, so prepare. We have derived the Magnus Force formula for a spinning ball of radius a. We have derived the pressure formula, and this is the whole thing. Using a domain decomposition, computing the left-hand side. Yes. And the second part of computation. The velocity, this is for the reader, and actual force from the pressure term and from the velocity term, and this is the result for the Magnus Force. Ooh, wow. So I hope you enjoyed this video, and maybe next time in other kind of series maybe I will find more in this topic. I think this is the Saint Grail or something like that, because I think this is the result which I have not seen anywhere. So please let me know if you find the result for the Magnus Force on the internet. I will be really grateful if you do, but I will be, I think, more grateful if you won't, if you will not. So I think this is the end of our video, and I will just end the video. So Panther I will add to the end, and see you next time.